Hopefully we got everybody online. Looks like we got Coy. Good morning, Coy, or good evening, Coy, or whatever it is. It's evening there. Um, yeah, so let's get to it. I wanted to start by just working an example of the limit comparison test because we didn't quite have time for that last time. So just to remind us, uh, this was the statement of the limit comparison test. We got two non-negative sequences. We look at the ratio of their limit, or the limit of their ratios. And three cases come up. If the limit's between 0 and infinity, then it's pretty straightforward. And then case 2 and case 3 are the sort of slight oddballs that we deal with when we get there. So the example I wanted to use, because I'm evil, is this. Why? You just fell for the converse trap. The sequence sign of 1 over n definitely converges to 0. But does that mean that the series converges? Not necessarily. Okay, so this isn't that easy, unfortunately. But we are going to need that limit. So it is certainly true that it definitely does not. Well, okay, let me say this correctly. We have that tells us that it for sure. I don't know. Let me say it this way. I don't know how to word this. So I'm just not even going to say it. Let's just do the problem. Um, English is hard. No, I can't say it in French either. Mm. Yeah, so this limit is what? It means that the sequence part converges, but that doesn't mean the series does, right? Right, because remember, what is a series? It's a sequence that's built out of the partial sums of another sequence, right? And just because the sequence 1 over n, sine of 1 over n converges, doesn't mean that the series converges. It might, okay? Yes, because this limit converged to 0, that means that the sequence sine 1 over n converges to 0. But that doesn't mean the series does. Okay. Now, here's what was trying to say earlier, but English is failing me. What would have happened if that limit was non-zero? Then the series would diverge, right? So remember the nth term test. If the series converges, then the limit is 0. But if the limit is 0, can you conclude the series converges? No. But if it's not 0, you can conclude it diverges. Well, take the limit first if you think maybe it, yeah, just right. But in this case, that didn't help, right? Because we got 0, so that doesn't tell us anything. Now, we will need this limit here in a minute. Now, for other reasons. Why is that limit 0 anyway? I mean, it is, but why? Yes. Yeah, sine is a continuous function, so sine, or the limit of a sine is the sine of the limit. What's 1 over n do as n goes to infinity? Gets to 0, right? And what's sine of 0? Fun. Okay? All right, is that good? All right. Now, what kind of values does sine of 1 over n have? Because what was the hypothesis on basically any of the things that we've talked about with series thus far for most things? Am I allowed to have negative terms? I'm not. Or am I? Not now. We will today, later. We'll allow to have negative terms. Um, but up until now, am I allowed to have negative terms? Does this series have negative terms? It's signed, so you think it might, but I've been really evil. Ah. What's the starting value of n? 1. So what's the first value of my sequence? Sine of 1. What is sine of 1? No. Sine of pi halves is 1. Sine of 1 is? No. Come on, guys. Okay, do I actually care what number it is for right this instant? What do I care? If it's positive or not, or 0. Okay. Is it 0? Why not? Because when is sine equal to 0? At 0 and pi and 2 pi and 3 pi and 4 pi and 5 pi and so on. Is 1 equal to any of those? No. Okay, so it's not 0. Is it positive, Jack? Why? Because 1 is in the first quadrant. Okay, when I say 1 here, I need to be careful. What is 1? Keep talking. Uh-huh. Right. Yeah. All right. So what Jack's saying is, well, pi halves is 90 degrees, right? Well, if pi is 3.14, let's just call that 3, because we are in Indiana after all. You guys know about that? Oh, nothing's wrong with Indiana. That's what's wrong with Indiana. Read. Mm-hmm. Can't do it. The bill written by the crank Edward J. Goodwin implies various incorrect values of pi, such as 3.2. Well, basically, yeah. Well, so this guy was a crank. So a crank is somebody who discovers quote unquote false mathematics, um, and then is convinced that they're brilliant. So what he was really trying to do was um, he wanted to, because he discovered these amazing things, so to speak, he wanted the Indiana legislature to pass a bill recognizing him as the discoverer of this, and in exchange for doing so, he would allow Indiana public schools to teach this material free of charge, basically. Except he was a crank, and this is not, in fact, true. Yes, so anyway. Um, okay, but joking aside, let's just say that pi is equal to 3 for number crunching purposes. Pi halves would be 1.5. 1 is going to be somewhere over there, right? And in fact, I can tell you a little bit more precisely where it is because 1 radian, this is really cool. One radian is the angle that makes the arc 1 unit. if the radius is 1. That's how the radian was defined, right? It is pretty cool, right? Yeah, no, it is gnarly. Okay, anyway, so it's definitely positive, right? Okay, now as n grows, what kind of values? When n is 2, I'm taking the sine of a half and then a third and so on. And so the sequence of values is going to go, let me pick a different color. Start here, or well, it'd be the y value of there, and then here, and then here, and it's going to converge to that value here. And what is the y value of that big old blue dot? Big times 0. Okay, so I trolled Aunt Salty on Monday because she looked at this and she's like, wait a minute, this isn't a positive sequence. And I was like, yes, it is. And she's like, oh, you even. Yeah, so I trolled Aunt Salty. She thought I had made a typo on the sheet, but no, I was just being evil. Okay. All right, so it is a positive sequence. Yes, exactly. Well, there used to be these things. This is how you used to get a job in like 16th century Italy, is you would like challenge a sitting mathematician who had a professorship to a math duel, and if you beat them, then you got their job and they got fired. Right. Yeah, it would be, but it's also a lot messier. Burr. Yeah. William Burr. Yeah. Um, okay. So anyway, so it's definitely a positive sequence. So how does the limit comparison test help us here? Well, what do I need to do? I need to compare this. I need to compare this series to some other series. I had to choose this other series. What would be a good series to pick? That's tough, Cole. That's not a series. That's a number. Well, no, 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 a series, right? So I've got a big old sigma there, right? Sigma of what? Phone a friend. All right, well, you got 5 to choose from. Jack's got it. All right, Jack. Huh? You could, but this is like the ending scene in the Holy Indiana Jones and the Last Crusade, right? Choose wisely. Okay. Um, well, look at what we have, right? I claim that the thing that you want to pick is appears in the series in question. Well, we've got sine of 1 over n. What about if we didn't have the sine? Let's just do 1 over n. Sounds. Oh, yeah, totally, right? All right, well, let's just see what happens. All right, what does that series do? Uh, no, we don't know what the first one does yet. That's the whole problem. The sequence goes to 0, but that doesn't tell me shit about the series. Does the series converge or diverge? It diverges because the p-test or because of that RM proof we did, right? Which series is that? That's the harmonic series, okay? Yeah, no, seriously, that we've proved that twice now, right? The p-test, what does the p-value have to be? Bigger than 1 to converge? What's the p-value here? 1. Is 1 bigger than 1? So it diverges, okay? All right. All right, so if I want to do limit comparison, I need to do the following. I need to examine this limit. Hmm? Uh, we'll find out. We're not done yet. Yeah. So if we're going to do the limit comparison test, well, we need to do a limit comparison, right? So we need to look at what is the limit of that fraction. Fair? Okay. Well, how do we do the limit of that fraction, pray tell? Thank you, Kim. So, first off, is this of the form 0 over 0 or infinity over infinity? Over 0, right? All right, so I like to write, I'm using L'Hopital's rule by putting an h under the equal sign, okay? So what is the derivative of sine of 1 over n, Kim? Cosine of times call, phone a friend, huh? Antiderivative. What? Phone another friend. Thank you. Why is it that? Well, chain rule. Right. Yeah, yeah, my door, right? The door to my office has the comic on it, right? With me sort of South Park style, holding a stick, saying you have to use the chain rule, right? So what's the derivative of sine of 1 over n? Cosine of 1 over n times the derivative of 1 over n. What's the derivative of 1 over n? Negative 1 over n squared by the power rule. Yes? Okay. And if I have to get my stick and beat that one into you guys, so help me. Because n to the minus 1, power rule, dude. And have the same thing in the denominator because what's the derivative of 1 over n? Well, we already answered that question, right? Mm-hmm. Excellent. Well, that's very nice because what happens to these negative 1 over n squareds? Poof, right? Poofly poof. Because this and that cancel. And so I'm considering really, well, good. Since you like where it's going, where is it going? What is the value of that limit? The inside is. Ah, yes, thank you. Right? So the inside 1 over n still goes to 0, but this time we got cosine of it, so it goes to cos of 0, which is 1. Okay, so the L value is 1. Is that between 0 and infinity? Last time I checked. Hmm? Come on, Will. You have to tell me that you wake up every Monday, Wednesday, Friday filled with joy that you get to go to McKinney's class. Unending, undying, relentless joy. Mm-hmm. Yeah. Now, if I can only get you to be this joyous on the other 4 days of the week, maybe three. I'll leave Sunday to yourself. But Sundays I'm most joyful. I get to go be with the Lord. But you can't be. Well, what about being with me? That doesn't make you equally joyful. Um, not quite. I'm being facetious, right? Right. There's just some differences between you and Jesus. Probably just a few. All right. So, what does the limit comparison test say? Right? If the limit is between 0 and infinity, then the given series and the thing we're doing the comparison with do what? The same thing. Hence, both of these series do either both converge or both diverge. But the series that we compared to, what does it do? It diverges because it's the harmonic series, right? Hence, so what does our given series do? It diverges. Yes. Okay. But see, at the beginning, we didn't know that 1 over n, the series, had anything to do with it. Well, the sequence did, right? But so we had to choose a series to compare it against and go through some rigmarole to find out that, okay, so let me rephrase. The series 1 over n diverges. That's definitely true. Okay. But that's not enough. What I also needed to know was what's the limit of the ratio of the sequences? And what did I get for that limit? 1. Okay. But point being, I got something between 0 and infinity. I got a positive number. So because I got a positive number, that said that the two given series either both converged or both diverged. But we already knew one of them diverged, and therefore the other one had to also diverge. Then I would have had to, let me go back over here. Then I would be dealing with either case 2 or case 3. Possibly, right? And yeah, then I would be dealing with either case 2 or case 3. Okay. Or it's also possible, because notice that case 2 and case 3 require you to know that the B sub n series either converges or diverges. What about if you've got a limit of 0, but your B sub n series diverges? Can you say anything? No. Okay, that means you didn't choose wisely. Try again, right? I mean, you can't do that in well, yes, in the Indiana Jones movie, right? If you choose poorly, then you like turn to sand, right? You chose poorly. Yeah. Okay. So yes, but you would be in case 2 or case 3 if that happened. Okay. Or you picked a bad thing to compare against. Okay. So the B sub n, the other series, is a series of your choosing. And I mean, I'm not bringing up Indiana Jones just because trying to be coy here, but like you really do have to choose that second series in a smart way. No. Well, okay, is there a rule? No, because if it were that simple, then like math isn't that simple, unfortunately, right? There is a choice, and so how do you learn, or like how do you know what to choose? Spidey sense, right? Well, okay, intuition, yes. Right, but how do you build that intuition? Doing shit tons of problems and being stumped and then figuring it out, right? That's how mathematics is done, right? There's a famous mathematician, he's passed away many years ago, but Paul Erdős, he was Hungarian, and he He once quipped that a mathematician is a machine for turning coffee into theorems. Right? Give the mathematician coffee, they process the coffee, output theorems. Yeah. But that comes with significant amounts of ass and chair time. Okay. So, anyway. All right. Well, yes. All right. So, where's my pencil? Oh, it's there. Okay. All right. So, good. Now, we're going to talk about two new tests. Okay. We're going to talk about what's called the ratio test and a related test called the root test. I'll start with the ratio test because it's the one that I think in practice I tend to use much more. Um, so, uh, well, okay, I'll go ahead and I'm going to say this slightly different than the book. Um, you know what? Actually, no, I'm going to stick with it. Okay, so I'm going to define a limit of a ratio, hence the name ratio test. But the ratio I'm going to look at is not, there's no other series here. I'm just looking at the series by itself, okay? And what I want to look at is what is the next term divided by the previous term, okay? All right. Well, if I've got a positive sequence, what are the possible values for this limit? What's the smallest it could possibly be? 0. Okay, what's the biggest it could possibly be? Infinity. And it could be somewhere in between. All right. Where is the split point here? It turns out that it's at 1. Okay. So we have 3 cases. If that ratio is less than 1, then the series converges. If that ratio is bigger than 1, the series diverges. And the fun one is when it's equal to 1. If r equals 1, you can conclude nothing. And I'll give you a couple of examples to demonstrate this. Exactly. So if you get 1 for this ratio and you are sure that you correctly got that limit, then this test doesn't tell you anything. But there are still plenty of other tests on the table, right? So that means you picked the wrong test. Try one of the other ones instead. Hmm? Oh, goodness. Well, let's see. We've got the p-test, the nth term test, the comparison test, limit comparison test. It could be geometric. It could be telescoping. The ratio test, the root test. A lot. All of those. All the ones that we've talked about. Yeah. I mean, I'm not going to test you over a test that we haven't talked about, but there's a lot. Okay. Yes. Yes, Jack. Huh? It's very much related to it. Um, and that's actually one of the reasons that we use R here, right? One of the differences, though, is that with R equals 1 in the geometric series, what happened? It diverged, but that's not the case for the ratio test. Okay, so no, you're right. And in fact, the proof of the ratio test uh, comes from doing kind of a comparison to a geometric series. Um, so they're very much related. Yes. But the other parts are very similar looking. What's the one difference between this, the way I've written it here, because this is the way the book writes it for this section, and the ratio, I mean, sorry, the geometric series? Okay, so that was the p-test, right, where the middle value was in one of the categories, or, well, p-test and also the geometric, was that r greater than or equal to 1 was the divergence case. But with the geometric series, was it okay to have both positive and negative terms? Yeah. Okay. So the geometric series the stuff that we talked about, the sequence didn't have to be positive. It could be positive and negative. Now, next time, we'll start to allow our sequences to be both positive and negative again, and we'll actually talk about. So think of this as ratio test part one. We'll do ratio test part two for how to doctor this up to talk about positive and negative series later. Okay. So yeah. So the geometric stuff is the only situation that we've done thus far that has both positive and negative terms. Okay. So now let's do a couple of examples here. Um, okay. So let me look at 1 over n factorial. And let's just make sure we're clear. What does the exclamation mark mean? Okay, so what's the factorial function? So what's 5 factorial? 5 times 4 times 3 times 2 times 1. Okay, so it's a descending product. You can think about it recursively, and we'll actually need to do that here in a minute. Okay. And you know what you need to do to understand recursion? You first must understand recursion. Okay, so the factorial function, um, there's a couple ways you can think about it. 5 factorial or any integer factorial would be that times that minus 1 times that minus 2 dot 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 all the way down to 1. Um, if I think about it recursively, uh, then that's the recursive definition. And what makes this recursive is, um, so a recursive function is a function that references itself. Okay. Um, so how many of you guys have ever had the experience of when you look something up in the dictionary and it tells you to go look up another word, and then you go look up that other word and it says to go back to the first one, right? That's recursion, right? So recursion is the only word in the dictionary that's allowed to be defined in terms of itself, because that is the very concept of recursion. Yeah. Yeah, well, we do. Okay. Let me show you guys this. Okay, so if you Google recursion, it says, did you mean recursion? Well, yes, I did. Did you mean recursion? Yes, I did. Did you mean recur? Oh, great. Now you know what recursion means. Okay. Um, yeah. So, anyway, why I want to think about this recursively will become clear in a moment, but the recursive definition of it is any recursive process needs to have a base case because you can't have infinite recur. Well, you can mathematically, but you can't on a computer, which is where we normally talk about recursion. So the base cases here are 1 factorial is 1. That perhaps isn't a shock. But we also define 0 factorial to be 1. Does that bother anybody? It does? Okay. Here's how I like to think about why that makes sense. Let's suppose that Cole has 5 t-shirts and he's going to pack them in a suitcase. And how many different orders are there for them to go in the suitcase? Well, how many choices does Cole have for the shirt that goes on the bottom of the suitcase? If he has 5 t-shirts, he has 5 choices, right? So he folds one up. I'm going to assume that you fold your clothes before you put them in the suitcase rather than just stuffing. Oh, roll. Okay. Well, yeah, it is. Okay, let's just say you fold them though, right? So you fold it, put the first t-shirt in. Okay, how many choices does Cole have for the next t-shirt to put in? 4, and then 3, and then 2, and then 1. And those are independent choices, so the number of arrangements is 5 times 4 times 3 times 2 times 1. 5 factorial. Okay, so if he has 5 shirts, there are 5 factorial arrangements. If he had 10 shirts, there's 10 factorial. If he has 0 shirts, how many arrangements are there in his suitcase? There's 1. Namely, he doesn't have anything to put in the suitcase. Huh? That's how I like to think about it. I mean, the other way to say this is that I define 0 factorial to equal 1, and the rest of you could just shut up and accept that. Right? I mean, I could be a jerk about it, right? But there is a good reason why 1 is what it's defined to be. Okay. So, whenever you see a factorial in a series, 999 times out of 1,000, the ratio test is the way to go. Okay? Because of the following property. So what do I need to do the ratio test here? What is a sub n? It's that, right? 1 over n factorial. All right, so what's the limit I need to compute? I need to compute a sub n plus 1, which is what? Divided by a sub n. Okay, but I wrote it as multiplied by the reciprocal just to be swifty. Okay, it's easier to write. Okay, do you guys accept that this is the limit that the ratio test demands that I examine? A sub n plus 1, that's the first fraction, divided by a sub n, that's the second fraction. Oui ou non? Mr. Kim says oui. Mr. Trepp says oui. Monsieur Michalski, oui ou non? Oui? Oui ou non? Oh, so the ratio test demands that we look at a limit, right? What limit? A sub n plus 1 over a sub n. Is that what I wrote down? A sub n plus 1 divided by a sub n. What is a sub n here? 1 over n factorial. So a sub n plus 1 would be 1 over n plus 1 factorial, where the is the parentheses, right? And then what's a sub n? 1 over n factorial. And if I divide by a fraction, I just can flip and multiply instead. Yes, Mr. Snyder.
So our equation is that plus 1 for the whole a sub n or just the n?
The n. Yeah, good question. So let's look back here. It's a sub n plus 1, not a sub n plus 1, right? So I replace n with n plus 1. Okay, so I get this. All right, here's where the recursive property is so handy. What is n plus 1 factorial? It's n plus 1 times n factorial. Okay, so stare at that for a moment and convince yourself that that's true. What is n plus 1 factorial? Can I write that as n plus 1 times n factorial? Why can I do that? That's the recursive property of factorial, right? So 6 factorial is 6 times 5 factorial. Yes? So n plus 1 factorial is n plus 1 times n factorial. Why was that a brilliant thing to use here? Because look, idu, looky, or so idu is the ancient Greek word for that, which it's really fun to translate that as looky. Okay, but really, what does it mean? Behold, right? Well, at least that's how it tends to be in New Testament translations, right? Because looky in New Testament translations says a different ring to it. Um, yeah, so those cancel, and I'm just now looking at the limit as n goes to infinity of 1 over n, which is what, pray tell? Or sorry, n plus 1. Thank you. Is 0. You know, Donovan, why is it you picked like literally the worst seat in the house?
I thought it'd be cool because I'd be closer to you, but it's not that cool actually.
Yeah. Well, that's like 4.2 Rontgens. Not great, not terrible. I know that one's not funny. So, haven't you guys saw the HBO miniseries Chernobyl? No, it's actually really good. Although there's one episode that I had to like skip parts because it was just too painful to watch. Anyway, but one of the guys in there, the like dude that's tasked with trying to deal with the aftermath, finds out, 3.2 or 4.2 or whatever the number is, Rontgen, which is an amount of radiation. Not great, not terrible. Turns out that that was the maximum amount that the Geiger counters or the measurement devices that they had on site could measure. And it was actually like 100 times that. So, yeah, Chernobyl was bad. Um, Chernobyl is a textbook example of how not to run a nuclear reactor. Yeah, yeah. Well, forever, no, but millions of years, right? I mean, they're within 30, 40 kilometers at least is basically an exclusion zone, and you can only go in there for, a few hours at a time still. Well, you'll the amount of radiation you'd be exposed to is starts to get higher than sort of an acceptable dose per year. You'd be at increased risk of cancers and other things. And of course, the closer you get to the core, or what's left of it, um, is yeah. Of course, now it has. Well, we can talk about Chernobyl later, but anyway, um, 0. Okay, is that less than 1? Okay, 0 is less than 1. So by the ratio test, this series that we started with converges. Okay. Well, no, this was our first example of this new rule.
So because it's 0.
Mm-hmm. And 0 is less than 1. No, the series doesn't converge to 0. Mm-hmm. Okay. In fact, this particular series converges to the number e. Huh? Why do I do this to you? Why e? Okay, now that one, next week I'll be able to demonstrate why. No, because I started at 0. Mm-hmm. Brilliant! Fortunately, there's a wall behind you. On the ledge, the windowsill. Yeah, that's dangerous physics, man. So, okay, so that's the ratio test. Now, so my hints here for the ratio test are, if you see a factorial, do the ratio test to start. Most of the time it works out. Okay. Now, there's a related test to this called the root test. And Ansaldi has a typo on the sheet, which I need to fix. Um, Basically, you look at the nth root of a sub n rather than these ratios. Um, and that's another approach to it. I'll let you guys read about that. It works very much the same as the ratio test. Um, it's, I think, less powerful than the ratio test, but sometimes more convenient because the algebra works out nicer. But anyway, now I'll give you another hint when not to use the ratio test. If your series is, if the sequence is a rational function, so that means polynomial in terms of n divided by another polynomial in terms of n, if you do the ratio test, you will get 1. Rational, meaning it's a polynomial of n divided by a different polynomial in terms of n. Okay. Well, it doesn't have to be a polynomial. It could be a radical function too. But if you do something that looks like that, then what's going to happen is by L'Hopital's rule, you'll get 1 every single time. Well, but that's exactly when the ratio test is inconclusive. Okay. So, yeah, so for example, if we did the ratio test with 1 over n or 1 over n squared, we would get 1 in both cases. But what's the series 1 over n do? It diverges. What's the series 1 over n squared do? It converges, right? So, but both of them have a ratio test limit of 1. Okay, so this is why it's inconclusive, because there are some series for which that ratio test limit of 1, you have divergence, in other cases where it's convergence. Okay, all right. Is that kind of Gucci? All right. Well, we should probably quit. So, look at the root test stuff in the book. It's not that much different than the ratio test. Um, and if you guys have a question quick at the beginning next time, we can talk about that. And we'll continue on Friday with more stuff, more tests. Yeah. All right. See ya.